morning. Welcome to the final day. So I've got a list of thank yous, a few announcements for things coming up today. Then Sid will be introducing our final plenary speaker, and that should wrap us up. So first of all, I'd like to start by thanking again Shutama Buntham for all of her wonderful, wonderful arrangements. Round of applause again for Shutama. And also Stancy Curtis, is she here? Over there, Stancy, for all of the arrangements in here. But I'd also like to thank Bill and Michael and the industrial track organisers and Jeff and Doug, the president at the back there, and especially to Julie Youngblood and to Jeannie Gerber, who's been on the registration desk all the time. A round of applause for everybody there. Most of all, I think we should really show our appreciation for the wonderful people at Tradewinds. They've been phenomenal. People like Jim and Margarita, they've just been absolutely always there for us whenever we've had any problems. They've been there in seconds. So please, big round of applause to show your appreciation for Tradewinds. So I think it's been a wonderful conference. Everything's gone pretty well, I think. Food's been good. Everything seems to work well. I would personally like to come back again here in the future. But if anybody would like to turn up at the business meeting today at 1:30, which is this room, everybody's invited, everybody gets a vote, and you can give us all of your feedback on what went right, what went wrong, what you'd like to change for next year. That worked. We need to hear it. Because everything that was good about this year is because of the feedback we've received in previous years. So please come along 1:30 and tell us. After the business meeting, we have the wine tasting, which is
3 doors down.
3 doors down.
Same hall.
Okay. Lunch today is going to be in the breezeway, which is next to the courtyard. So just keep walking that way for about 20 yards so we get some AC today for the lunch. Is that right, Stan?
Yes.
So I think that wraps up everything. Oh, after the talk, after Christina's talk today, we're going to have about a 10-minute presentation from Michael, who is conference chair for next year, and he'll be telling us all about FLAIRS2013. Michael, would you like to stand up so everyone can see you and grab you and shake you around? We can give Michael a round of applause as well. Okay, so that wraps it up from me. Over to Sid.
So let me just start by asking everybody to give a round of applause to our great conference chair, Phil. Okay, so it gives me great pleasure to introduce Dr. Cristina Conati, who is an associate professor in computer science at the University of British Columbia in Vancouver, Canada, where I'm told she's always 4 blocks away from the beach. So she has flares every day. So Dr. Conati does work in this interdisciplinary arena encompassing artificial intelligence, cognitive science, computer science, and HCI. And she really tries hard to integrate these different areas, and you can see this because she's an associate editor for the International Journal of AI and Education, ACM's Transactions on Intelligent User Interfaces, and IEEE Transactions on Affective Computing. So it's very rare to get people who fuse these different areas together, and I think nobody does it as well as Dr. Conati. Today we're going to hear a presentation by Cristina on user adaptive interfaces. We all know that this one-size-fits-all approach works for no one. So her work and the work of her colleagues are going to try to make interfaces that are dynamically sensitive to the needs of users on the fly. I hope I got that right. Let's give a round of applause to Dr. Conati.
Told that I should speak in the microphone. Okay, so for first of all, thank you, Sid, for the very kind introduction, and for the organizers for inviting me at this conference. It's my first time at FLAIRS, but I definitely, I'm appreciating the quality and the beautiful setting. So I think I definitely have a good sense that I might be coming back. So thanks for that. And so as Sid was saying, I will today talk about this quest of user adaptive interaction that essentially is, understand who are the user of the interactive system and what the interactive system can do for them. And as Sid was saying, the field of user adaptive interaction is an interdisciplinary field that combines research in artificial intelligence, human-computer interaction, cognitive science, with the goal of creating user interfaces that can really improve human-computer interaction by providing a personalized experience to the user. And we want to do that. I mean, you can do that by giving the user the choice on how to select things around and how to customize, but that sometimes can be quite difficult. So this field tries to take the opposite approach of trying to allow the system to also have an awareness of what the user's needs might be and try to provide suggestions that can help the user personalize the interaction in the right direction. So just a quick little tutorial on user adaptive interaction. The adaptation cycle essentially consists in collecting as much input as we can from the user interaction, use that to generate some inferences on user states that could be relevant to adapt the interaction to the user needs, and then generate some adaptive behaviors based on that assessment. And in terms of what should go in a user model, there can be a variety of different states and user traits depending on what the goal of the interface, what is the goal of the support that one wants to provide. But people have been working on modeling goals that the user is trying to achieve during the interaction, knowledge that the user has about the domain, behavioral regularities, preferences, and even more esoteric things such as cognitive states, emotional states, metacognitive skills, and so on and so forth. In terms of input, some obvious ones could be to get self-reports and questionnaires from the user, but as you can imagine, that's not sustainable. You cannot do it all the time. So it's also, a lot of the research goes into trying to get the information that is needed in the student model in a more implicit way that relies on behaviors that are naturally occurring in the interaction, such as interface actions, obviously, gestures, gaze recognition, body movements, and so on and so forth. And in terms of adaptive interventions, there is a variety that people have been working on, but they can go from providing explicit help on a given task that the user is trying to accomplish, adapt the interface layout and functionalities so that they are more prominent for what the user is trying to do, tailor information presentation, how the content that we want to show to the user is presented, recommend objects, and the list could continue, but I guess for the purposes of this brief illustration, I think that's sufficient. And so adaptive intervention, work on user adaptive interaction has been going on, I would say, for probably 20 years at this point, and has been shown to, have success in a variety of applications. And just to name a few, could be recommender systems, desktop assistants, intelligent tutoring systems that have been, this conference is a very good tradition on having tracks on intelligent tutoring systems, so many of you might be familiar with this field. In this talk, I will focus, I'll try to give you, show you what user adaptive interaction is about by giving two examples of research that we have been conducting in our lab. And the first one is providing adaptive support to human learning in open-ended interactions. It's specifically with interactive simulations, and this is part of research in intelligent tutoring systems. And I also talk about something different that's called user adaptive visualizations. That is a pretty novel way to try to apply the concepts of user adaptive interaction to information visualization. So we'll start with providing adaptive support to learning from interactive simulations. And just before we move to that, I just want to give you a brief overview of what intelligent tutoring systems are. So intelligent tutoring systems are user-adaptive systems that have the goal to provide better learning experience, personalized learning experience to the learner. And so essentially, the way it works is that usually they're usually known as, being AI complete, because there is so much representation and reasoning that needs to go on to allow a tutor to have performances that can resemble the performances of a human tutor in terms of adapting to users. But usually there is a model, a domain model, that essentially represents all the concepts, procedures, ideas that we want the student to learn. There is a pedagogical model in which the tutoring knowledge is represented in terms of teaching strategies, remediation strategies, the curriculum that one wants to teach. There is the student model, that is essentially the user model that I was talking about, where again one can represent a variety of information for the learner, such as knowledge, goals, beliefs, emotions. This information is leveraged by the tutor to decide what to do with the student. So going to the cycle in which the tutor decides what is the next tutorial action that needs to be taken. For instance, select an activity for the student to perform. The activity is presented to the student in a given interface, and an ideal ITS would have a communication model that has all this great information on how different learners might like to see information presented, and how to present it, of course, should be also, see if I can try this. Yes. If this could be informed by information in the student model. Oops. I think I was too bold here. Okay. And then usually part of the intelligence in the intelligent tutoring system is that not all answers are predefined. The tutor has the ability to generate answers to activities and problems presented to the student, starting from the domain model and by using some inference mechanism. So the tutor can generate a solution to the activity that the student is trying to generate. The student in turn generates some solution. These two are compared, and abstractions are made by the system to update the student model, which in turn feed back into the tutor, which continues in the tutoring cycle by possibly selecting another activity, providing hints, feedback, corrections, and there is a variety of things that the tutor can do at that point. So, I just wanted to give you a sense of the complexity of this technology. To my knowledge, the ideal tutor that has all these components working really well hasn't been built, but there's a lot of people doing great work in, filling all the different boxes. So I think we're not far from the ideal tutor. The point is, in the last 20 years, research in intelligent tutoring systems have really achieved really great accomplishments, and there are nowadays intelligent tutors that are being deployed in schools. Specifically, Conati Learning out of Pittsburgh has, intelligent tutors that are used in, at this point, hundreds of thousands of high schools in the United States. But a lot of these tutors focus on a specific type of learning, that is problem solving, where students are given problems to solve, and the tutor kind of monitors the student as the student generates a solution and provides help when the students seem to be lost or needing help. And it's called coach problem solving. One feature of this particular type of interaction is that in general, this problem solving has been used in domains such as physics, computer science, statistics, so domains that are known as well-defined, because usually there are well-defined problem solutions that the tutor can use to track what the student is doing and providing feedback. And there is usually also quite clear definition of correctness. That means what it means for the student to generate a correct or incorrect action that the tutor can leverage to provide feedback. Okay? And this is just an example of what it means. This is like a tutor for physics, Andy, sorry, I forgot the reference, but essentially a physics problem is given to the student needs to draw a free body diagram, type equations, and the tutor has a representation of what is the correct solution, can recognize correct or incorrect solutions, and provide feedback appropriately. And coach problem solving is great because it's a very necessary step in student learning. But there are also other instructional activities that can help learners with different learning styles, or even the same learner but at different phases of the learning process. And some of these activities include activities that are less structured and less open and more open-ended at problem solving. And people have looked at a variety, but in our lab, we, for instance, we looked at ways to provide intelligent support to learning from examples before you even engage in problem solving, learning by exploring interactive simulations, and learning by playing educational games. And today I will focus mostly on some work that we have been doing on how to work with interactive simulations, but all these activities have in common the challenge that they are more, what the learner can do is more open-ended and well-defined than in more traditional problem-solving settings. So there's no clear definition of what is a correct behavior, and there's also no clear definition of what is an effective as opposed to ineffective behavior in terms of generating learning. So it's very hard from an AI point of view to create models that the intelligent tutoring system can leverage to track what the student is doing and provide necessary feedback. Just to give you an example of what I'm talking about here, we have a suite of interactive simulations that we have developed in our department to help students learn AI algorithms. And it's open source, you can go and use it. We use it all the time in our AI courses. So if you just Google AI space, you get to that page. We have a selection of algorithms for search, constraint satisfaction, Bayesian networks, neural networks, and so on and so forth. And I'll just show you one example of an applet that supports constraint satisfaction. In particular, shows the working of the AC3 algorithm. And so essentially, AC3, probably most of you know it, but it represents a constraint satisfaction problem in terms of a graph where the variables in the constraint satisfaction problem are nodes with associated domain values. Constraints are arcs between the variables. And the way the algorithm works, essentially, it goes through, cycles through the arcs, that is, through the constraints, and verifies if that associated variables are consistent, meaning if domain values for those variables are consistent with the actual constraint, and if not, those domain variables get pruned, and this process essentially tries to bring the problem to a state in which at least the basic wrong domain values have been eliminated. You might even get to a solution, or at least to a constraint satisfaction problem that is easier to solve. And just to show you how this works interactively, so a student can use this find step functionality, for instance, to see step by step how the algorithm works. So the algorithm picks an arc to validate, like the blue arc down there. Oops. It decides that it's not consistent, and it makes it consistent by pruning, and it turns green because it prunes the domain variable values that were not consistent with that particular constraint. The student can also use step. It's a more high-level way to run the algorithm, because those 3 steps that I showed you are done together. The student can also just run the algorithm to completion, just let it run and see how the different arcs are chosen and how they're made consistent. The user can stop, can reset the problem, and there are other functionalities that are not. There's more actions that the user can do that are not really relevant or not important to give you the sense of what I want to say today. But the point that I wanted to make by showing that demo is that really the student can do all these functionalities, and the student can use them as she pleases to explore how the algorithm works. There is no right or wrong. When we give it to the students for homework, we just say, try a variety of examples. We can point out 2 or 3 that might be, on the easy, difficult, medium spectrum, just to help them. But otherwise, it's just really pure exploration. It's great. The problem is that not all students, this is a very well-known result, not all students work well in this open-ended. They need more structure. They might get lost. They might not really know how to explore in a way that really brings to clear learning. So it's important to provide adaptive support for those students who need more structure. But because of this lack of clear understanding of what are the good behaviors that we might want to foster and what are the detrimental ones and what is correct or incorrect done in this environment, we don't know. So the question is, how do we model what the students should do? And even more importantly, how do we provide adaptive support that fosters learning without actually interfering with the open-ended and student-led nature of this interaction? Students want to explore. That's the great side of interactive simulation. You don't want to make it too didactic by turning it again into sort of like a structure to the activity, but you still want to provide help with when needed. So that's the kind of balance that we want to strike. So our approach is to try to model what are the behaviors that are important to capture via data mining, and also to try to increase the bandwidth of the information that we use in the student model by using more innovative input devices, and today I'll focus on describing some of the work that we've done in using eye tracking. So just a high-level description of how this behavior discovery is done. Essentially, we take action logs and other data that is available during the interaction. We create vector of interaction features that describe essentially summary statistics on how the user uses the different functionalities in the system. Do clustering on this. We have some papers that describe the details of how the clustering is done, but I won't have time to go into the detail of that today. And essentially, this clustering gives you groups of students that have similar interaction behaviors. Okay? We also apply association rule mining to these clusters to have a sense of what are the behaviors that are, in terms of interface actions, that are actually defining being a member of that cluster. And so these are distinguishing behaviors that we're sort of looking for. And usually what you want to do is try to create a mapping between these clusters and learning. And you can do that if you have performance measures that you can have a priori by running user studies. You can use that. But even if you don't have performance measures, experts might be able to look at the clusters and the behaviors and try to come up with a mapping to learn. Okay? And so we've tried this approach on the CI Space applet. We ran a study where we had 64 subjects, so it's not big data, but it's enough for our purposes for the time being. The students looked at material on the AC3 algorithm using the textbook. Then they took a pretest to gauge their understanding on the algorithm. They worked with 2 problems with the CSP applet, and then they took a post-test. So we collected over 13,000 actions and about 17 hours of interaction. And the features that we used included frequency of usage of the different types of actions in the interface, and also do latency in between actions, because that gets a sense of how much they're thinking about what they're doing. And we used mean and standard deviation. Standard deviation gives a sense of the spread or consistency of their behaviors. There are 7 actions that we looked at, so that turned into 21 features. We found 2 clusters, and there were statistically significant differences in learning gains in between the members of the 2 clusters. So we call them high learners and low learners, just for reference. And if we do the data mining on this cluster, you don't have to parse those boxes. I have an English description of the rules, but some sample rules that we found of the behaviors that describe users in these clusters include, for instance, members of the high learner clusters use direct or click. Oh, actually, I forgot to demo this. So when you use the applet, instead of just running, stepping, and letting the algorithm choose which arc to select, users can actually say, try to do arc consistency on this particular arc. So the user decides which arc should be selected. And high learners do a lot of that, which kind of makes sense because it's a more proactive way to interact with the simulation, okay? Low learners, on the other hand, show the opposite behavior, some of them. They don't do that direct or click that much. They tend to let the algorithm choose what to do. And when they do direct or click, they don't spend too much time in between subsequent clicks. So they seem to be clicking around but not taking the time to think. Okay? So these behaviors seem to be, after you look at them, quite intuitive why they belong to high or low learners. Okay, but what do we do with this? A lot of people do data mining, and we've seen even yesterday, data mining to kind of mine behaviors and then provide it to designers to see how the system could be improved, and that's very valuable. But we want to go a step further. We want to use these learned clusters and the rules to actually build a user model that can classify new users based on the new users' behaviors, okay? And then, based on the classification and on the rules that are detected as being responsible for the classification, we want to use these detected behaviors to provide adaptive support by discouraging the detrimental behaviors and encouraging the good ones. So, just to put this on the schema, we take the clusters as essentially our training classes, association rule mining, and we build a classifier that as a new user comes in, we incrementally build a feature vector that describes the behaviors of this particular user. That's fed into the classifier, which in real time generates a classification for the user and also returns the rules that were responsible for that classification, which essentially identify the distinguishing behaviors of that user. And these can be used to generate adaptive interventions because, for instance, if a user is categorized as being a low learner because it tends to not use this direct or click functionality, one might generate a suggestion in real time to try to encourage this behavior, okay? Or if we know that the user pauses very briefly, it does direct or click, but then it doesn't, it does it too quickly, we could generate interventions to actually try make the user slow down. And how to do that, it's another problem, but conceptually you can do that. So what I want to show you here is, okay, can we do this classification in real time? Because essentially you want to try to predict learning as soon as possible to generate the intervention soon enough that they can make a difference in the interaction, right? So this graph shows given percentage of observed actions. So we run simulations. This is based on we leave one out cross-validation, but we run simulations by feeding to the classifier just the percentage of incrementally of the actions of a whole interaction from each user in the set that we have, and we calculated the accuracy for each specific subset of action seen essentially, and already after 28%, seeing 28% of the action, the overall accuracy, the black line, is meeting the baseline. That essentially baseline predicts the most likely class, which here was the low learners. And then after seeing about 46% of the actions, the accuracy goes above 80% for each class, low learners and high learners. And it's important to have a balanced classifier because you want to be able to distinguish them, okay? Let's see. So, using action only is great, so we're already getting quite interesting results, but I want to talk a little bit about additional work that we've done by using gaze data, adding that to the actions. So we ran a similar study, but same design, but now we actually track the user gaze with this Tobii 120 eye tracker that captured gaze movements in real time. And it's non-intrusive, so this is the face of a user working with the CSP applet using this Tobii T20 that is essentially embedded in the monitor, so it doesn't touch the user at all. See if I can start this. And this just shows you, the user doesn't see this obviously, it's just a functionality that exists in Tobii that allows you to see the traces of where the user is looking at. Those red dots were the fixations where the user was looking, and then it showed you the trace, the temporal change of the fixation positions. So, monitoring gaze data, using eye tracking to understand gaze behavior, it's a quite well-established field. Usually, the way gaze data is processed rely on these basic notions on fixation, so exactly where you're looking on the screen. And the eye tracker gives you the duration of the fixation. In this case, the size of the dot represents that. Then there are saccades, there are actual movements that take you from one fixation to the next, okay? And measures that can be used to extract information on gaze patterns include things such as number of fixations during a certain interaction, fixation rate, duration of fixation, length of saccades, and things such as angles between two consecutive saccades or between a saccade and the horizontal. And this gives a sense of how spread around is the gaze, for instance. And there are other measures that include looking at specific areas. So these are general measures that are independent from what is on your screen. But if you know what the user is looking at, you can generate areas of interest that represent salient points of the interface. And then you can take measures that relate to, say, proportional number of fixations in a given area, proportional time spent, time to first fixation, and so on and so forth. And then you can generate features to feed to a classifier by taking the sum, the mean, standard deviation. Here we have 51 features overall. Areas of interest that we have used include the top bar, where the user makes selection of what functionalities should be used. This message panel that essentially narrates what's happening during each action of the AC3 algorithm. The graph itself, and another panel that narrates a different functionality that I haven't discussed. So if we merge, I won't go through the whole process again, but if we apply the process that I showed earlier to the combination, to a vector that it's made of features of combine action and gaze data, what we see is that already after seeing 20% of the interaction data, including gaze, the classifier beats the deadline, and the baseline. What am I talking about? And actually, both the high, for both classes, high learners and low learners, the accuracy is already over 80%. So we can do more accurate classification earlier, okay? And if we compare, for instance, we tried this exercise of comparing classifiers that use only action information, as we did before, just gaze information, and gaze plus action. And as you can see, if you look at overall accuracy over both classes, the gaze plus action does a little bit better, but nothing significant. But then if you look at the two individual classes, the strength of the gaze plus action is that it's much more balanced. Okay, because essentially, even for low learners, it achieves high accuracy early on. Okay, as opposed to the brownish bars, there are the action, where it's very high for low learners, but it's doing quite a bad job for high learners. Okay, so I'm gonna skip this. Oh. So we have been working on, so I've been talking about user modeling for open-ended and unstructured interventions, where the challenges from the AI point of view is really, how do I model, characterize, and work with these behaviors that I really cannot even define a priori? And we mine the relevant behaviors using data mining, and we have very encouraging results with the CSP applets. We have identified clusters of behaviors that map onto learning. We show that we have an online classifier that achieves good accuracy pretty early on, so you can actually use it to build adaptive interventions. Obviously, it's not 100% accuracy, but that's a problem with most user models, so you have to deal with how to present information, knowing that you're almost never 100% accurate. And we've shown how eye tracking can help. And the other point is that with this framework, adaptive interventions can be derived automatically, because the framework also gives you rules that indicate what are the behaviors they should be focusing on. Okay? And this is something that we're currently working on, and I can talk about it if during the discussion if you're interested. And what I want to say is that we're currently also applying this to different interactive simulations that someone is using in the physics department. They collected a lot of data of users working with those simulations, and we're applying exactly the same paradigm to see if these results actually transfer. Okay, and I can also talk about that if you're interested. So now I want to switch gear, abandon for a little bit for today the ITS component of the research, and I want to talk a little bit about this user adaptive visualizations project that we've been working on and we're pretty excited about. So why, I'm kind of stuck here with this microphone. So why do we want to look at user adaptive visualizations? Well, the field of information visualization is a very well-established field, very successful in creating visualizations that can help people see information in a very compact and often useful manner. The problem is that traditional visualizations are designed with this one-size-fits-all paradigm in mind, where what you know is the data that you want to represent and the tasks that one wants to support, and then the visualization is designed accordingly. However, what about user differences? The user hasn't been taken into loop much in this field. But there is increasing evidence that individual differences actually matter. It's a lot of text on this slide, but this is just to give you a few references. You know, all you should pick is the things in blue. So there is evidence that users might have different preferences with working with alternative visualizations. There's been, quite a lot of evidence on the impact of domain expertise, and now you can deal with specific visualizations, spatial cognitive abilities, and other perceptual abilities, including perceptual speed and visual working memory, can also affect how someone works with a visualization and the performance outcomes. And even more surprising, there's quite a quite strong body of work showing that even personality traits can affect specifically preference in working with alternative visualizations for the same task, okay? And specifically, it's a locus of control personality trait. I can tell you more about it if you're interested. So our long-term goal, given all these results, is that we want to sort of, bring the concept of user adaptive interaction to information visualization. So leverage input sources that we can have when users work with a visualization, and you cannot get away with gaze data because it's a mostly perceptual task. If it's an interactive visualization, you can also leverage information interaction events and build user models that essentially can give the system real-time detection of user traits and states that might indicate that the user needs help working with a specific visualization, okay? And that could include relevant cognitive skills such as perceptual speed, expertise, instant signs of confusion, cognitive overload, and so on and so forth. And the forms of adaptation that, in general we should consider include either providing help for the user to deal with a current visualization if for some reason the user is stuck with that, or even recommend an alternative visualization if that exists and if it makes sense to make the user switch. Okay, so these are two alternative approaches, but they both go along the lines of improving what the user does with available visualization tools. So, as I was saying in the introduction, it's a fairly new domain of application for the concept of user adaptive interaction. There has been some previous work where people have looked at, in terms of what was modeled, user preferences on a variety of available visualizations, domain expertise, and capturing suboptimal behaviors that could be predefined a priori. Using mostly action data, so the work that has been done with interactive visualizations without using gaze. And adaptation, people have mostly looked at how to switch and suggest alternative visualizations when the user seems to be not working well with the current one. What we're looking at, so the work that I described today looks at different sets of properties for the user model, including user cognitive abilities, and also trying to capture and model the type of task that the user is trying to perform and task complexity. We'll look at gaze data, and in terms of adaptation, we're currently focusing on providing help with a specific visualization as opposed to switching to a different one. So I'll just briefly talk about a user study that I'll use to show some of the results that we have on how we can detect and create the models for interaction with user adaptive visualization. So the study that we ran had three main goals. The first one, gain further evidence on the impact of individual differences on visualization processing, because some studies exist, but they related to specific visualizations, and we wanted to see if these results generalize to different ones. The second goal was to see whether if there is an impact of individual differences, does that come out in the gaze patterns that the person uses by looking at the visualization? And also, can we detect and model in real time relevant user characteristics and task characteristics from gaze data? Okay? So today I will just talk about these two goals here. The third one, there is a paper that you can read, I can send you if you're interested. So we had 35 participants working for about an hour. It was a within subject design, so all participants did all the tasks, and they also had their gaze tracked by a Tobii T20 eye tracker. So they were tested for relevant user characteristics using standard psychology tests that exist. We didn't design the test, we just took them from the literature, and I'll show you what these characteristics are. Then they had training with two visualizations that we were focusing on, and I'll describe next. Then they do a battery of visualization tasks with these two different visualizations to see how they would perform using the two different tools. And then in the end, they also took a questionnaire on which visualization they preferred and how they rated the two visualizations in terms of ease of use, because we also wanted to see not just pure performance in terms of task accomplishment, but also preferences. So in terms of user characteristics, we look at perceptual speed and visual working memory. Perceptual speed essentially gives a measure of how quick you are at processing visual information on the screen. Visual working memory is more related to capacity of storing and manipulating the visual information. And there are standard tests that are like minutes short that we can use to test these guys. And we used them because they were used in previous studies and they were shown to impact visualization performance. So we wanted to see if they also affected the visualization that we are using. Then we also looked at verbal working memory, a new one, because in a visualization there are often verbal components such as the labels, the legends, the question text, and so on and so forth. And the last one, we also looked at visualization expertise. People have looked at expertise in the domain of the data that is being visualized, but here we wanted to see if there is an impact of how experts the users are in using the visualizations that we make them use, okay? And so the two visualizations that we used are the radar graph and bar graph. They're two visualizations that are considered equivalent in showing, in doing tasks that relate to comparing a set of variables or series on a variety of dimensions. Okay, you can read them here, but here, the task that we used, I have a larger version in the next slide, but essentially here, for instance, these visualizations relate to how students, what are the grades, and of course grades of students on a variety of subjects such as physics, geometry, and so on and so forth. Okay, and the black line, the black bar, or the black line in the radar graph represent class average. So you want to compare student marks against class average. Very simple task. We had users do 5 different tasks with each of this visualization. These are standard tasks that come from visualization literature. They're considered building blocks for visualization processing and include retrieving value, a specific value, like the score of a specific student. Filter, I'll show you what it is, compare computer-derived values, doing computations with whatever information you're retrieving from the graph, find, filter, and find the stream and sort. I'll just show you 2 examples of these guys just to give you a sense. So one sample task is filter, and the user is given this visualization, and there is a question there that says find the courses in which Alex is below the average and Mark is above it. They have a sequence of choices they can select from, and this is the right one. And find extremum. So filtering, essentially, you give the constraints on the data that you want to retrieve, and you have to retrieve the data that satisfies the constraint. Find extremum is find that data point that has some extreme characteristic. Here, for instance, in which course does Alice deviates most from the class average? Again, the user can choose the answer, and the answer is this one. Okay, just to give you a sense. So simple tasks, and they did it in 2 different levels of complexity. So they repeated them, and this is all counterbalanced to make sure that there are no ordering effects. But essentially, simple tasks, you compare only 1 student against the average, and to increase complexity and to see that there is an effect of complexity, we also included 2 students, compare 2 students among themselves and among the class average. Okay? So, first of all, just a summary. I won't go into all the details of the data analysis, but in terms of goal 1, so first of all, we wanted to see, is there an impact of the individual characteristics that we tested for on performance over this task with the different visualizations, okay? So what we found again a result of perceptual speed, where perceptual speed impacts completion time for both visualizations, okay? And they're always faster using bar graphs, but perceptual speed, the higher the perceptual speed, the faster is task completion with both visualizations. But there is an interaction effect. Users with low perceptual speed suffer more when they use radar graphs. Kind of understandably so, because they're more complex. Then we found 2 interesting things, but these results were already found in a previous study with different visualizations, so that's nice. But we also found that working memory affects user preferences. We didn't find any impact or significant impact on performance, but we found an impact on user preference where there was an interaction effect. Users with higher visual working memory gave higher preference rating for radar graphs. They didn't do better, but they seemed to like them more than users with low levels of visual working memory. And verbal working memory impacted ease of use, which was an alternative orthogonal dimension that we asked about. So interaction effect, users with lower verbal working memory gave higher ease of use ratings to bar graphs. Okay? So we have these results. What do we want to do with that? Well, let's see if we can use the information that we have from the user, which is gaze essentially, to see if we can detect these characteristics in case we want to provide help based on that. But before that, in order to provide help, you also need to see if you can detect what the user is trying to do with the visualization. Okay, so we also want to try to predict the tasks. And just quickly show, essentially, we collected the same similar gaze data as we did for the previous study. So this is the user working and doing tasks with their gaze tracked. So the features that we used are exactly, with some minor differences, but essentially is exactly the same general features that we used in the previous work that I showed you, okay? Obviously for AOI related features, the AOIs are different because of course now they're looking at a different display. Just to give you a sense what the AOIs are here, there is an AOI that is called high area that encapsulates the part where you actually look at the values of the different bars. Low AOI is just for consistency, is the bottom parts of the bars that essentially contain no information. The labels for the different series, the question text, and the legend. And we have similar ones with, of course, different topologies for the radar graph. Okay? So classification experiments, what we're trying to do. We're trying to infer task type. So what is it that they're doing, which task they're trying to do at a specific point. Retrieve value, the 5 ones that I showed you earlier. Complexity, simple versus complex. And also we're trying to predict cognitive abilities, high, low perceptual speed, visual working memory, and verbal working memory. Okay? We look at 2 feature sets just for experimenting. One is feature set that has all the features, those that are general and those that are based on AOI. Then we also looked at how much can we predict if we have no AOI information. So you only have general gaze patterns that you can look at. Classifier, we tried a few we didn't do any fancy machine learning. We just looked at different classifiers in Weka and we found that the logistic regression was the one with the best results. So these are the results that I'm going to present. Comparison with the majority classifier. So we start by seeing if we can predict the 5 basic tasks that are retrieve value, compute the right value, filter, find the extremum, and sort. And So here the baseline is the bluish line at the bottom. The full is the green, and the results of the classifier without using AOI information is the purple. So the classifier with the full features beats the baseline throughout, and after seeing about, and sorry, we did exactly what we did earlier. So here we are checking what is the classification accuracy if, given that the classifier sees incremental portions of the gaze data, as if it was the case if the user was incrementally working with the visualization, okay? So this is accuracy over time based on how much data the classifier sees, okay? So after, do I have the line here? No. The classifier reaches an accuracy of about, 60%, goes above 60% after seeing 70% of the data. So it's not too early, but considering that it's based on gaze only, it definitely beats the baseline. But the AOI information is needed, because if I have no AOI information, the accuracy is definitely very low. What we found looking at the confusion matrix is that there were recurring confusions between two sets of these tasks. One is the right value and filter, because essentially some of the tasks that we gave them essentially were doing filtering and then doing some of the right value based on the results of filtering. And between find extremum and sort, because often if you want to sort, you need to find the extremum first, right? So, and this is something that was actually commented in the original paper that we used to build these 5 tasks. They were acknowledging that some of these can often essentially be part of another, right? So we decided, well, let's just try to combine the ones that were highly confused and see what, they become different higher level classes of tasks, essentially. So at this point, if we only do 3, obviously it's an easier classification task. So the baseline, so we have a much improved accuracy. So after 40%, seeing 40% of the data, the classifier really reaches about 70% accuracy in predicting the tasks. But AOI information is still needed, okay? And the last one, predicting task complexity, whether they're looking at a complex versus an easy task, so the task where they had to compare 2 students against the average versus tasks where they only had to compare 1 student. This is, easier because it's a binary classification task. The baseline is higher. They had to do more simple tasks than complex tasks during the study, so that's why the baseline is not 50-50. It's not 50%. So it's a high baseline, but the full data classifier with the full data set still beats it, and it achieves, it has already a quite good accuracy of 75% almost from the beginning, and then it goes above 80%. And the interesting thing is that here it's a binary classifier, so it's easier to see what are the actual predicting features. And here, for complex tasks, what we see is that predicting feature is time spent in and transition to legend. So the more complex task has more of that, because essentially given that the whole layout is more complicated, it takes more time for the user to create the mapping between the legend and the task, okay? And the other thing, the last thing that I want to talk about is, I said we want to see if we can predict in real time their cognitive measures in terms of perceptual speed, visual working memory, and verbal working memory, okay? And we get this funny looking learning curves given the incremental amount of data that the classifier sees. So we see this pattern where there is a peak of accuracy quite early on, and then the accuracy goes down. So what we think is that essentially cognitive traits really have a strong impact in when you first look at a visualization and you start making sense of it. Create all your mappings, you look at the legend, you look at the labels, you look at the text, and figure things out. After that, when you start doing the task at the level of, for instance, comparisons or more specific retrievals, then the perceptual abilities kind of wash out a little bit. Okay, they become more difficult to detect. And it's interesting because the top predicting features from the logistic regression are different from the different traits, and they kind of make sense. So for visual working memory, the top predicting feature is first fixation to how long it takes the user to look for the first time at labels, text, and high AOI. And these are really crucial parts of the visualization. High AOI is where all the information is in terms of the data values. The text is the question, and the labels is what are the series about, right? For verbal working memory is time spent on the text of the question, which also makes sense, right? Users with lower working memory about, sorry, I didn't say this, but the users were been into high and low cognitive abilities, so the tests return actual scores. So you can try to predict the scores, but that's difficult. So we just split users into high, low, per ability user using a median split. Sorry, I didn't say that. Perceptual speed is percentage of fixation time in the legend. So perceptual abilities allow you, if you have high perceptual speed, you don't need that much time to create that mapping between the legend and the graph, okay? So, we're very excited about these results because first of all, we kind of found further confirmation that individual differences are important in information visualization and one should take them into account. And also, we have quite strong evidence that gaze data can be used as a source of data for making useful predictions about users looking at visualizations in real time and to build on those predictions to possibly generate adaptive interventions. And here, I should really point out, the machine learning that we used was very simple. We didn't try anything trying to find, improve the algorithms. We didn't look at anything in terms of looking at more temporal information, for instance. So I think there's a lot of room to improve those accuracies that are not really that great from the point of view of, can I reliably build interventions on those accuracies? We were beating the baseline, but that doesn't mean much in terms of practical utility, right? But we did perform the baseline, even with partial observation, so that's always good. And then we found that we have different gaze features as predictors for different abilities and for different, for instance, for complexity. And one can build on that information to try to get an understanding of what are the components on which users might need help as the interaction proceeds, okay? So in terms of current work, just real briefly, now we're looking at how and when to provide these adaptive interventions. So in terms of how to provide this intervention, we are focusing on providing interventions to help users with a specific visualization. We don't want to switch for now, okay? So we're looking at the study to compare 4 different ways to highlight information on a visualization. We're looking at the radar graph, at the bar graph as an example. And these are ways to highlight information that come from the literature. So we have a quite complex study that tries to see if different designs work differently for users with different abilities. And another one that we're very excited about is when to provide the how do we know when to provide the interventions? I mean, we might detect that the user has a low perceptual speed. Okay, fine, but even a user with low perceptual speed with a specific visualization might not need help. You don't want to just provide help when it's not needed. So how do we know when a user really needs help? So we're running the study. Don't look at the visualization, it's too complicated, but it's a more complex visualization that we have used up to now. And we are trying to collect data points to have a data set of labels in which we know that the user is confused by working with this visualization. And also this visualization is interactive, so it allows us, this study will allow us to see what happens in terms of classification accuracy for user modeling when we put together actions and gaze data. And so some future work, how to build real-time detectors of confusion and confusion triggers. You're confused, why, and what can we do with it? So how to intervene to reduce confusion and what other cues and states should be considered to decide when to adapt, such as cognitive load, but that's related to confusion. So, and what other long-term traits and states should be considered for adaptation. So we're very excited. There is there's a community that is building around this field. We have a workshop organized on user adaptive visualizations, organized in conjunction with a conference on user modeling, adaptation, and personalization, which is one of the main venues to present this kind of research. So if you happen to be, around Rome during that time, you want to come, And it's not located in that ruin area. It's a different, but it's a nice picture. So to conclude, finally, so I just wanted to convey the message that user-adaptive interaction is a very exciting and thriving field of research. And if you're doing research in AI, this field, in my view, has a great potential to show how AI can make a difference in improving human-computer interaction. Okay? I'm just mentioning here some exciting avenues of research in addition to the ones that are already presented that people might want to work on, and there's already work going on, but I think there's still room for a lot of exciting research there. So, how to increase user control and awareness during this kinds. A big problem with user adaptive interaction is like, oh, but the user loses control. They can be intrusive. They can be confusing for the user. That the paperclip didn't set a very good start for this field, the infamous Microsoft paperclip. But essentially, going very much towards a sense of a mixed initiative interaction, where the system provides suggestion based on user modeling, but the user is still in control. There could be a dialogue and exchange on why you're suggesting that, or and the system could try to provide explanations on why certain inferences and certain suggestions are being made, right? So, I see a lot of room for, putting more natural language in these kinds of conversations. Obviously, leveraging big data that becomes available and ever-increasing availability of sensors that can give more information about the user. I talked about eye tracking, but another one that's becoming very popular, and someone just told me it's also very cheap, much cheaper than eye tracking, is EEG. So sensors that essentially monitor directly brain activity. So give you a much direct window of what the user is thinking. Applying concept of user adaptive interaction to social media. There is already quite some interesting research done there. And then user adaptive environments, not just interaction with computers, but there's sort of like ubiquitous, context-aware environments where your appliances in your room can be a user adaptive environment, monitoring you and providing you the services that you need. So I want to end by concluding by thanking all the people that helped me with this work, actually did most of the work. And I also want to thank you for your kind attention. Thank you very much.
So we have time for several questions.
Yes?
Very interesting, thank you. I work on the HCI, and I'm curious about the variance of the result that you're showing, because all these graphs, they show the mean accuracy, I guess. But how much certainty do you have about those accuracies? Like we could create a bands of variance to get those accuracies.
Yes, I don't have that data, but so you mean in the cross-validation, what was the...
Right, because you cross-validate, but
Yeah.
you can do many times, so you can get an idea of how you're sampling essentially from a...
Yes, you're right. Yeah, we should add that. I don't have the data off the top of my head, but
That would be a great addition, I think.
yeah, that's it. Yeah.
So I have a two-part question. For the first part of your talk, when you discovered the patterns, the rules that discriminate high and low,
Yeah.
have you all done any work on what are some ideas on the actual adaptation to those rules?
Right. So one thing that we're trying to do, for instance, how to generate these suggestions to slow down, for instance, or well, let's put them together here. But essentially, suggest to click on direct or click. So my student did a few pilot studies on one experiment by giving a little hint, verbal hint, and then following up with a verbal hint plus highlighting the components when they could click if they follow the verbal hint. So the pilot study was interesting because he was using a specific way to highlight the arcs, and it turned out that the users were not looking. They didn't notice the intervention. So now is experimenting with a different one, possibly blinking. So, but we are at that level at this point, really, how to make them salient without making them too intrusive. I mean, you could force the user to start following the suggestion by making that the only thing that they can do, but that's too intrusive, right? So how to make them noticeable and convincing without again being too forceful. It's something that we're working with. Yeah.
And another question was pertaining to this really cool field of user-adaptive visualization. You mentioned that there's quite a bit of evidence showing clearly that user characteristics matter.
Yeah.
I wonder though, just a question, how big are those effects? So for example, let's say visual working memory is a significant difference. Are those in the talking seconds or are they big?
The effects are not huge. But again, these are very short tasks, right? So you could say piled up and coming from the different aspects of perceptual speed, visual working memory, verbal working memory. The tasks here are very short. So, but that's a good question. The effects on their own are not huge, but these are very simple tasks, right? So the more difficult task more difficult visualization that we're working with now, it's a tool to support decision making. So they have to spend more time. Essentially, they can change weights of different alternatives and see how that impact value of the overall decision. So they actually spend more time on the task, and it's definitely more challenging, even in terms of the complexity of the visualization. So we're pretty convinced that the effect sizes will be higher there. So these two, I mean, they're proof of concept, but they are simple visualizations and they were simple tasks. So, but that's a very good question.
Any other questions? All right, we have time anyway, so.
Yes, I guess one.
Go ahead.
I was wondering if in the visualization task you are looking also into the affective state of the user, have an impact as well.
Yeah. So this idea of monitoring confusion is actually, so confusion is one of the official affective states. So that's what we're exactly trying to capture. So essentially, we're asking users, but we need the data set, we need the label data to know how to build these classifiers. So essentially, in this particular study, we're asking users to provide. There is a little thing that we call the confusion button that we ask the users to press every time they feel that they are, there is some sort of problems in them looking at the visualization and processing it. So we are really hoping that we are collecting enough of those data points so that we can start building the classifier. We also interview them afterwards to see what are the sources of confusion, because we would like to be able to build classifiers that can predict that they are confused and why they're confused, right? But confusion is just one of the emotional states. I'm sure there could be others that we could look at. This was the most obvious one that we could think of as a start, but if anybody has suggestions along those lines, we definitely, this is really just the start. All right, great, thank you very much.
Thank you.